Bismillahirrahmanirrahim. Contents of our today's lecture are: today we will discuss effect of transmission line compensation devices on the distance protection. Here in this category we discuss impact of series capacitors, series reactors and shunt devices, and then we discuss loadability of relays, a very important concept regarding the characteristics of different distance relays characteristics. Then we discuss protection of parallel lines, challenges that are to be addressed while providing protection to the parallel transmission line. So we discuss effect of zero sequence coupling. I have excluded this topic for now because it requires a lot of drawing, so which is not possible here in online session. That's why this time I have excluded this from the course. So here we will discuss the second one, the incorrect operation of directional ground fault relay in parallel transmission line. And we will discuss incorrect operation of phase distance relays in case of parallel transmission line. So these two challenges of parallel transmission line protection has been included into the course. So at the end of this lecture we will complete the chapter number 5 as well as contents of CLO3, which is related to the protection of transmission line. Now let's start our discussion regarding effect of line compensation devices. So first of all we discuss the series capacitors. Here in this one line diagram, a series capacitor have been shown with the transmission line. Okay, according to the calculation and analysis, the most feasible place for this series capacitor for line compensation will be the midpoint of the transmission line. But that is not possible to do. Due to this reason, capacitors are normally installed at one end of the line, either at the start at substation A or at substation C. Here on this line A to C, this capacitor has been installed on substation A, where we have installed relay RAC as well. So this relay RAC is a distance relay. So first we will discuss what is the purpose of this series capacitor. Series capacitors are used to compensate the line series inductive reactance. So in other words, it will reduce the line impedance. So that is done to increase the line loading capability, to improve the line voltage regulation, as well as to increase the system stability. So these are the reason for which we install a series capacitor in long transmission line. Okay, so to achieve these advantages. Now on the other hand, there are problems or challenges associated with these associated with the protection of such line which have a series capacitor installed. Now let's discuss what are those challenges. We will explain this concept by drawing all these parameters of line and capacitor and operating characteristics on RX diagram. Here is the line impedance from A to C. A is our reference substation where we have installed relay RAC, and C is the other end. So that's why impedance is starting from 0 at A and maximum line length at C. So this is the line impedance A to C. So relay characteristics, if we assume that we are using our directional admittance relay which is inherently directional. So here is a circle which is passing through the origin. So it's zone 1 which is set to provide protection up to 85 to 90% of line length. So as zone 1 is set to provide protection to a fraction of the line length which is from 85% to 90% of the line length. So here we can see this thing on the RX diagram as well. If this line A to C is being protected by this relay RC up to this point, on this RX diagram, this point will be the point of intersection of line impedance and the relay characteristics, this point. Next, right after this capacitor at point B, where will be this point B on RX diagram? Here it is to notice. Look here, this is a capacitor which has a negative reactance. So that would be in along this vertical axis in downward direction. So the point B due to this capacitor will be here on RX diagram. It means the point just after capacitor lies here at point B on RX diagram. That is due to the negative reactance associated with the capacitor. Now, what happens to the line impedance as we move from point B onward up to the other end of the line? So total line impedance has been shifted downward due to the presence of this series capacitor, because at relay installation point A, impedance seen by the relay if a dead short circuit occurs at point A will be 0. Then we have a series capacitor. Right after this capacitor, if fault occurs, that short circuit at point B, impedance seen by the relay will be at point B on RX diagram. Then if we move along this line away from point B, so here the locus of that line will be this dotted line. In other words, we can see here, due to the presence of this series capacitor, the line impedance has been shifted downward. Now this presence of capacitor has created a discontinuity in the line impedance, and that discontinuity exists at point A and B. At A we have zero impedance, at B we have a negative impedance, and within no time, within no distance. So what does it mean? It means a fault here, a short circuit fault right after the capacitor. This fault would be at point B on RX diagram here, which is clear from the diagram that this fault, which is very close to the relay just after the capacitor, will be outside the zone of protection of this relay RAC, which is a problem. A fault right after the capacitor would be considered as fault outside the zone of protection of this relay RAC. These are the challenges associated with the series capacitor on for distance relays. Distance relay which actually responding to the impedance up to the fault point would not be able to sense this fault. Now later here in this lecture, I will answer this question, how to provide protection in this situation where fault has been taken out of the zone of protection of relay. Next, if we start moving along this line from A to C in this direction, here we will reach at a point where the line impedance will just break into the relay operating characteristics. So this point that I have marked on the line will be here on RX diagram, where this dotted line impedance due to the presence of series capacitor is moving into the operating region of this admittance relay, this dotted point. So it means if fault occurs after this point on the transmission line, then our distance relay can sense this fault as fault in its operating region. But if fault lies here in this portion, which is between the capacitor point B up to this point where impedance has just moved into the operating region of relay, if fault occurs here, that fault will be considered as fault outside the zone of protection of relay RAC. So if we further move along this line from A to C beyond this point, a point will come where the line impedance, the line inductive reactance will become exactly equal to the line capacitive series reactance. So at that point, the line impedance will appear to be pure resistive, and this point on Rx diagram will be along positive R axis of Rx plane. So although line has inductance, but that inductance has been completely compensated by this capacitor up to this point. Okay, remember these series capacitors are used to compensate the line impedance, and the maximum compensation that we could achieve is up to the 70% of the line length. Okay, lines are never compensated up to the 100% of their inductive reactance. No. So maximum compensation that we can achieve is up to 70% of the line reactance. So now here one more thing to discuss. This is what happened due to the presence of capacitor. Capacitor has introduced a discontinuity in line impedance, due to which a fault, even a portion of the line, has been taken outside the zone of protection of distance relay. If fault occurs over there, distance relay would not be able to sense that fault. Okay, now the second challenge, look at this fault F2. For zone 1, this F2 is beyond its reach. Okay, that is beyond 85 to 90% of line length. So in other words, relay RAC is not responsible for this fault or should not operate for this fault. So this fault F2 along this line A to C in the absence of this capacitor will be somewhere here beyond the reach of relay RAC. But due to the presence of this series capacitor, as the line impedance has shifted downward, same would happen with this fault F2. This fault F2 will appear as fault inside the reach of this relay RAC due to the presence of this series capacitor. So the new dot that you can see on dotted line will be the position of this fault in the presence of series capacitor. So this is known as zone 1 of relay RAC has overreached, means sensed a fault beyond its reach due to the presence of this series capacitor. And we never want this relay RAC to overreach in zone 1, because zone 1 is always set to underreach. Zone 2 and zone 3 should be set to overreach. Now it is quite possible due to this overreaching, a fault in next line section may appear a fault in its own line zone of protection by this relay RAC due to the presence of series capacitor. So there are few things to be noticed in order to do the setting of relay RAC in the presence of this series capacitor. First thing, once we had installed a series capacitor, then make sure that consider this capacitor in service while selecting zone 1. So what does it mean? It means zone 1 of relay RAC would not be equal to 85% of line impedance AC. No, it will be 85% of line impedance AC plus the capacitive reactance. That would be negative and reduce the reactive part or inductive part of the line impedance as well. So whatever will be the combined impedance of line and series capacitor, that would be used for the calculation of zone 1 setting. So it means we have considered capacitor in service while doing zone 1 setting, so that relay should not overreach. If we ignore this capacitor, possibility is there in the presence of this capacitor, relay would start overreaching beyond the line section A to C for which it is there. So for zone 2 and 3, these two zones are set to overreach. So for their setting, we will ignore or we assume that capacitor is out of service. So when capacitor will be out of service, we will do zone 2 and zone 3 setting. When capacitor will come in service, their reach will further increase. So that is acceptable because zone 2 and 3 is already set to overreach. So in this way, setting will be done. I'm repeating it again. In case of series capacitor, zone 1 setting will be done by assuming capacitor in service. Zone 2 and 3, their setting is done by assuming capacitor is out of service. So we are doing setting in this way to make sure that zone 1 is always underreaching and zone 2 and zone 3 is always overreaching. Now we have addressed this problem. Let's come back to the solution of the first problem, that fault has been moved outside the zone of protection. For this series capacitor, there would be a switch in parallel to this capacitor that would be closed and open to take this capacitor out of service or bring it in service. When this switch will be open, so capacitor is in series. When this switch will be closed, capacitor will be taken out of service. So this capacitor, this switch in parallel with the capacitor, also used to provide protection to the capacitor. In case of this fault F1, we have a dedicated separated protection for capacitor as well, that we will discuss in chapter number 9, the protection of series and shunt capacitors. So that protection will operate and close this switch to bypass the capacitor from the system, because the short circuit may damage this series capacitor. Due to this reason, on the occurrence of a fault F1, we immediately close the switch in parallel with the capacitor to isolate this capacitor from the system. Once this capacitor has been taken out of service, immediately this fault F1 will move inside the operating region of relay, and then relay or AC will open the circuit breaker to clear the fault. So this is how fault would be cleared. Okay, I'm repeating it again. In case of this fault F1, which appear to be fault outside the zone of protection due to the discontinuity introduced by this capacitor. So how this fault is cleared? I said that RAC will not be able to detect this fault. So this fault would be detected first by the capacitor dedicated protection. So that protection will isolate this capacitor by closing a switch in parallel to this capacitor. Once the capacitor is out of service or bypassed, then this fault F1 will immediately move inside the operating region of relay RAC, and then relay RAC will detect it and open respective circuit breaker to isolate the fault. So although fault clearance has been slightly delayed, but that would be cleared in this sequence. First, capacitor will be isolated, bypassed, and then the circuit breaker will be operated by relay or AC to clear the fault. So that is the solution of this problem. Okay, now let's discuss the impact of series reactor on the performance of distance protection. Second device. So first I want to address this thing. What is the purpose of inserting an additional reactance in series with the transmission line? Okay, in those areas of power system where short circuit level is too high, to limit the short circuit level, it will become a requirement to insert a reactor in series with the line. So that is the only purpose of inserting an additional reactance, inductive reactance in series with the line impedance. Now let's see how this additional reactance would change the line impedance in RX diagram. To visualize this thing, we will use RX diagram. Here is line impedance, as we have seen in previous case, A to C. Relay has been installed at substation A. We can call it relay or AC. This is the relay zone 1 characteristic. Relay is providing protection to a fraction of this line length A to C up to this point that I have shown on line section A to C. And this point here on RX diagram will be the point of intersection of line impedance and the relay characteristic, this point over RX diagram. Now the presence of this series reactor will introduce a discontinuity in line impedance as well as the presence of series capacitor did. This time the presence of this reactor will move impedance of this reactor at point B after A. At A we have zero impedance. At B, right after this reactor, the impedance will move to point B. So the total line impedance will shift in upward direction. That have been shown with a dotted line, which is shifted in upward direction. So that is the discontinuity introduced by the series reactor. If a fault occurs right after this reactor, that would be a fault at point B. We can clearly see here, although discontinuity has been introduced by the series reactor as well as it was introduced by the series capacitor, but the fault right after this reactor does not move outside the zone of protection of relay. It still remains inside the zone of protection of relay. As we move from point B towards the other end of the line C, we are actually moving along this dotted line, which is a shifted line impedance in upward direction due to presence of a series reactance. We would reach at a point where the line impedance will move outside the relay operating characteristics, and here is that point on RX diagram. So what we have seen here, during the absence of this series reactor, relay was providing protection up to this point, and due to the presence of this series reactor, reach of relay has been reduced to this point on the line. Okay, so there is a reduction in the reach of relay due to the presence of series reactance. And in case of presence of series capacitor, we have seen that relay was overreaching, and here due to the presence of this reactor, relay is underreaching. Relay is not providing protection up to the point for which it was set to provide protection without this reactor. So what does it mean? It means this fault F2, that is within the zone of protection of this relay or AC zone 1, in the absence of this reactor, here is this fault F2. Now due to the presence of this reactor, this fault will move outside the zone of protection of this relay. Why it had happened? It is due to the presence of this series reactance, and this is known as the relay has underreached. Okay. Now as there is no issue in detection of a fault right after the reactor, so that's why we no need to discuss that thing. The only thing is how to do the setting to address this problem. Now we can see here the presence of series reactor has caused this relay to underreach. It means that is not a problem for zone 1. Zone 1 of relay is already set to underreach. It means while doing the zone 1 setting, we will always assume that series reactor is out of service, and then we do the setting of zone 1, which is 85% of line length. When this reactor will come in service, definitely reach of that relay will become lesser than 85%. Okay, that is not a problem for zone 1. But if we had assumed that reactor in service while doing the zone 1 setting, so possibility is there in the absence of this series reactor, zone 1 will start overreaching beyond the line length, which is not acceptable. Due to this reason, for zone 1 setting of relay or AC, we will assume that this reactor is out of service. Once it will be in service, relay will further underreach. That is not a problem for zone 1. And we do the in opposite way for zone 2 and 3, because zone 2 and zone 3 are always set to overreach. So due to this reason, we will assume that this reactor is in service while calculating zone 2 and zone 3 setting of this relay or AC. Once this reactor will be moved outside the system, out of service, their reach will further increase. So that is acceptable. But underreaching of zone 2 and zone 3 is not acceptable. So this is how the setting will be done in case of a series reactor. So short question could be asked in the exam to calculate the relay setting in the presence of a series capacitor or in the presence of series reactor. You should know this criteria, whether we will have to consider the capacitor or ignore the capacitor for zone settings. We will have to consider the series reactor or ignore the series reactor for zone setting. Third thing, that is shunt devices. So here in this diagram we can see here a shunt device which is taking a current IS. S stand for shunt. This is a shunt current drawn by the shunt device. This shunt device can be a shunt reactor that is installed in substation to compensate or overcome the impact of fronting effect, and shunt capacitors are installed to provide reactive power to the system in case of overloaded condition to boost the voltage. And in nowadays we are also using SVCs and other STATCOM devices. So purpose of those devices is to provide capacitive as well as inductive reactive compensation when required. So no matter what is the type of this device, whether it is shunt capacitor, shunt reactor or any other switching device, its impact on the performance of distance relay is not significant. Okay, why it is not significant? Reason is, when a fault occurs on the line, this IF current which flow in the fault and current which is available to relay IA, in the absence of this arrangement, IA will be equal to the fault current IF plus the current which is flowing towards the shunt device. Remember, this current IS is much smaller than this fault current IF. So the error introduced into the calculation of impedance up to the fault point is not significant, because this compensation current IS will be even lesser than the load current, and this fault current is much higher than the maximum possible load current. So in this way we can compare the magnitude of these two current. So that's why the sum of IF plus IS can be assumed equal to IF current, because IS is negligible. Okay, but if we are interested to have an accurate measurement of impedance up to the fault point, then this is the arrangement that you can see in the diagram can be used. What we have done over here, we have subtracted the current drawn by this shunt device from the current which is being provided to the relay here by this arrangement. Here connection of CT secondaries are done in such a way that current which is flowing towards the relay here downward, that is equal to the current IA, phase A current, minus current IS. So that would become IF. So it means current which is flowing towards the relay is only IF. The shunt device current has been subtracted from the CT secondary current. So what is the conclusion of impact of shunt devices on the distance delay? The shunt devices does not affect the performance of distance delays too much, and if we want to have our accurate response of distance delays in the presence of shunt devices, then this arrangement can be used, in which shunt device current would be subtracted from the CT secondary current coming from the system, so that only the fault current is being provided to the relay. Next we discuss this concept of loadability of relays, another very important topic. Question is always asked from this topic either in the quiz or in final exam. That would be a short question to calculate the loadability of relay. So that's why your attention is required. So this is a fact. As load on transmission line increases, the locus of apparent impedance seen by the relay approaches to the origin of RX diagram. So it means higher and higher the value of load, closer and closer the impedance seen by the relay will move towards the origin. So for some value of line loading, the apparent impedance will cross into the operating region of relay. So that is quite possible because operating region of relay will be around the origin. If it is impedance relay, the operating region is centered at origin. If it is admittance relay, operating region is passing through the origin. So this is how we define loadability of a relay. The value of three-phase load in MVA at which relay will be on the verge of its operation is known as loadability of a distance relay. Here we explain this concept of loadability of relays with the help of RX diagram. Now up to this point we have lot of know-how about this RX diagram. So now we can explain this loadability concept over here. So in RX diagram, horizontal axis is resistance axis, vertical axis is reactance axis. Let's assume this is a load line which has a power factor angle equal to phi, and if we keep it fixed, so impedance across this line will move towards the origin as load will keep on increasing. When we say that load is increasing, it means power in MVA as well as current in ampere both are increasing. Power and current increases due to reduction in impedance if we keep the voltage fixed. So as impedance is decreasing, that means our load is increasing. So if we assume that power factor is fixed, then it means the increase in load is equivalent to movement of impedance seen towards the origin along this line. Higher and higher will be the load, closer and closer that impedance will move towards the origin. So if we consider a line, so this is the line impedance A to B, okay, and if we have a relay characteristics to provide protection to this line, let's say the first relay, this is the characteristics of impedance relay and it has been shown with semicircle, so that will become characteristics of directional impedance relay. So it means we have combined impedance relay with the directional relay. So their common area of operation, that is this shaded portion, will become their tripping characteristics or tripping area, that is a semicircle. Because in lower semicircle, directional relay would not operate, and outside the semicircle, impedance is not going to operate. So the common tripping region of directional relay and impedance relay will be the semicircle, and this is known as directional impedance relay. So the radius of these relay characteristics, which is ZR, is the relay setting, the reach of the relay that we have set. According to the definition of loadability of the relay, this is the point on impedance line where the loading of the line has just reached a point where relay is at the verge of its operation. Mean if load will become further higher than that, this relay would respond to that load as fault condition, although that is not a fault because fault will occur along this line impedance A to B. Fault impedance and line impedance will be similar or same. So it means this value of load for which relay is tripping due to the line loading is known as loadability of a relay. So now let's see how to calculate this loadability of the relay. If we know the value of line to neutral voltage of the system and we know the impedance of the load that resulted this much load on the system, then we can calculate loadability of impedance relay by using this equation where SL, L stand for loadability of impedance relay, is equal to the line to neutral square of the line to neutral voltage divided by the impedance in the primary circuit, and that would be the impedance of the line plus load that has resulted this much load or current on the system, that the impedance seen have reached at the boundary of this relay operating characteristics. According to definition, the loadability is three-phase power. So that's why we have multiplied this calculated power with 3. So that will become 3 into single phase power, that is E square over ZP. Now let's convert this ZP into the impedance seen by the relay or on the relay side. That will be the secondary side of CT and VT. So the primary impedance, how much, and that impedance will be actually impedance from point A, the origin here, up to this point. How much is this distance? This distance is same as this value, the relay setting, because it is a radius of the circle. So radius of circle is equal to ZR. Now if we substitute the value of ZP in terms of ZR, that will become ZR into NV over NI. So that NV over NI when rearranged will become NI over NV in that equation. So the final form of equation is the loadability of relay is equal to 3 times of line to neutral voltage squared divided by the relay setting multiplied by Ni over Nv. Ni is the CT ratio and V is equal to VT ratio. Now the common mistake that students do in calculating this loadability is use of voltage, because data of this problem will be given voltage in line to line form. They forget to convert this voltage from line to line to in line to neutral formation. So they forget to divide this line to line voltage by under root 3 and then multiply with 3 as well. So their power will become 3 times of 3 phase power. So that is incorrect. If you want to use line to line voltage for the calculation, then omit this 3 from here. And if you are using a line to neutral voltage for calculation, then this 3 will appear in the formula. So don't get confused here in this. Next we see the characteristics of admittance relay, which is a circle passing through the origin of Rx plane, and the reach of the circle mean the diameter of this circle, which is the reach of the relay, is same as the reach of previous directional impedance relay. And according to the new characteristics, the loadability of this relay is load up to this point where impedance is reaching at the boundary of this relay operating characteristics. So definitely from the diagram we can see here, admittance relay have higher loadability capability as compared to impedance relay. It is better because larger amount of load will result in misoperation of admittance relay as compared to impedance relay. Okay. Now let's see how to calculate this loadability of impedance relay. We want to calculate this value of impedance, which has resulted load to break into the operating region of admittance relay. This is the angle known as maximum torque angle or the angle setting of relay, theta. And here this angle will be theta plus phi, and phi is the angle of power factor. So obviously from the diagram it appears to be theta minus phi, but I have written is theta plus phi because according to the convention this phi will be considered as negative for lagging load and this same phi will be considered as positive angle for leading power factor. So here if power factor will be lagging, impedance will be inductive and it will lie in the first quadrant, which is the case over here. We treat that angle, impedance angle or power factor angle, as negative, so that would automatically become theta minus phi. And if the power factor will be leading, so this theta will become positive and this line of impedance will move in fourth quadrant. So that will make this angle automatically theta plus n angle. Now impedance up to this point will be the projection of the ZR along this impedance line. So that is obviously ZR cos theta plus phi. So the loadability of this Moore relay will become 3 times E square, that is aligned to neutral voltage, divided by ZR cos theta plus phi, and this Ni over Nv, that is to convert the actual system impedance into the relay setting impedance seen by the relay on the secondary side. So these are the two formulas that we can use to find out the loadability of impedance relay and Moore relay. If we compare these two equations with each other, the formula to calculate loadability of impedance relay and formula to calculate loadability of Moore relay, we can see the only difference is this factor cos theta plus phi in the denominator of this equation. So the maximum value of this cos theta plus phi will be 1, and that would never happen practically. So otherwise this value will always be less than 1. That makes loadability capability of admittance relay higher than the loadability of this impedance relay, because we have a factor which is less than 1 in the denominator of this formula. This is from equation. From the graph you can see here, loadability of admittance relay is higher than the loadability of impedance relay. So further higher load handling capability can be achieved if we use a quadrilateral relay characteristics. Again we can see the upper line is passing through the same reach of the relay. Reach of all these three relay characteristics is same, but loading capability of this relay is further higher. Now you can have an idea how we decide the right bonding straight line of quadrilateral relay. So that line will decide the load ability of the relay, how much load relay can withstand without tripping. And further higher loading capability can be achieved by a modified admittance relay characteristic known as shape 8. It look like number 8, shape 8 relay characteristics, which has again the same reach, but the loading capability of this shape characteristic is much higher than the admittance and its counterpart impedance relay. We cannot compare it with quadrilateral relay because quadrilateral relay characteristics are flexible. We can modify this line which is bonding the relay operating characteristic from the right side to even have the loading capability greater than this shape 8 characteristics. So that's why comparison of this shape 8 will be with admittance relay and impedance relay. It has much higher loading capability as compared to impedance and admittance relay. This shape 8 relay is modified characteristics of admittance relay. So you can see here we have admittance relay characteristics plus offset admittance relay characteristic. When their characteristics are combined together, that will make a shape 8 characteristic. That is a relay characteristic designed to have very high loadability capability. So remember this problem of tripping of a relay due to loading, that occurs for zone 3 setting, because zone 3 setting has very large area. So normally load will break into the operating region of the relay. Due to this reason, for zone 3 setting we need this, we will have to address this problem of loadability. So for zone 3 setting, we normally use shape 8 characteristics or quadrilateral characteristics, which has much better performance or much higher value of loadability as compared to its counterpart impedance or admittance relay characteristics. So shape 8 relay characteristics are actually modified admittance relay characteristics. Two admittance relay characteristics are overlapping. One is a circle passing through the region, other is offset admittance relay characteristics. Okay, next we discuss the challenges in the protection of parallel transmission line. So when we are talking about the parallel transmission line, it means lines which are either sharing the tower, or if they have separate towers, they are sharing the right of way, mean they are in close proximity of each other. So distance between them is physical distance is not too much. So due to this closeness, there would be a zero sequence coupling between these two transmission line, and coupling in positive sequence and negative sequence will be negligible, because we know that there will be zero net field around the transmission line due to positive sequence current and negative sequence current. Reason is because the algebraic sum of positive sequence and negative sequence component is always zero. These three currents have equal magnitude and displaced by 120 degree, and their sum is equal to 0. It means the net magnetic field produced by the positive sequence currents and negative sequence current will be 0. But zero sequence current, that is in phase in all the three phases, will produce a net magnetic field around the transmission line. So due to this reason, magnetic field produced by the zero sequence current in one line will link to the next line which is in close proximity of that line. So that is known as zero sequence linkage. So first challenge that we discuss is incorrect directional ground relay operation. So here in this diagram, a line section have been shown, and there is a parallel line section AB. Remember, these two lines are starting and ending at different substation, but these two lines were sharing the right of way. Mean these were sharing the same corridor, same path, and were very close to each other, so that the zero sequence flux produced in one line is linking to the zero sequence into the conductors of the close by line. Here in this line section AB, we had used directional ground fault relay for the protection of this line. What does it mean? For this directional ground fault overcurrent relay, the polarizing quantity will be this current from the neutral. That is the reference. Why we have used this current as polarizing quantity? Because we have taken this current from a delta Y transformer where Y is grounded. Okay, so it will take the current from the system, here the system current fault, and the polarizing quantity is this IN. Same is the case on the other end of the line. Here these are directional overcurrent relays, and neutral current from here this transformer is being provided as polarizing quantity. Okay. It means this relay, which is relay at substation A, will observe a fault only in this direction. If a ground fault occurs here in forward direction, only then this relay would give a signal to this breaker to open. And relay at substation B will only detect a fault here in this direction. Definitely if fault occurs on the line, then the fault current from both ends will be in their trip direction of relay, and both the relays will sense this fault and operate their respective circuit breaker to isolate this line from the system. And next important thing, we have used these two neutral current at substation A and B as polarizing quantity because we know that the direction of this current will always be from ground to the neutral point of the transformer, like this. It means if neutral current is from ground to the neutral of the transformer and fault current is flowing from bus to the line, that is considered as forward direction of fault. okay, and relay would trip for this fault. Now what happens in line 2, if a short circuit occurs here in line 2, and that is a line to ground fault that has a zero sequence fault current, or a double line to ground fault which will result in a zero sequence current, then that zero sequence current here in this line will induce a zero sequence current due to the mutual coupling in zero sequence circuit here in parallel line as well. Now the path for the flow of that induced zero sequence current will be from line into the bus A, from this bus into the transformer Y connected winding, and from the neutral into the ground, and that current will flow through the ground and back into the transformer neutral at substation B in upward direction, and then back to the system. So it means this induced zero sequence current is going to circulate in parallel transmission line, because we had a Y delta transformer where Y is grounded on both sides of this line 1. So we have a closed path for the flow of zero sequence induced current. Okay, so now this induced current will receive these two directional ground fault relays. How it is going to receive? Now this relay which is at substation A would consider this current as fault current, because it is flowing from line to the bus, but the neutral current is flowing from the neutral to the ground. So it means the reference quantity and the fault current both are in compliance with the setting. So this relay at substation A would consider this condition as fault on the line and give a signal to its breaker to become open to clear this fault. Similarly, the directional ground fault relay at substation B would consider this fault current as a fault on the line, because current is flowing from bus to the line and the reference current is in proper direction. So due to this reason, the directional ground fault relay at substation B will also consider this condition as a fault on the line. But there is no fault on the line. Fault was in the parallel line at line 2, and that fault line has induced a current in this line, and both the directional relay has been fooled by this induced current, and line would be tripped, the line 1 would be tripped due to this induced current. So this is incorrect operation of directional ground fault relay. Now this is the incorrect operation of directional ground fault relay. What could be the solution of this problem? The only solution is we can't use the directional ground fault overcurrent relays here. We will have to replace them with some distance relay. Otherwise, these relays are going to be misoperated due to induced current. Now the second issue with the incorrect operation of distance phase relays. Here to explain that concept, I have built this diagram. Remember this bus A and B, both are also three-phase buses, although it look like a single-phase bus. Just to keep this diagram simple, I have made them a single bus but shown two lines in three phases, A, B, C, A, B, C. So these two lines are parallel transmission line on the same tower, are very close to each other. So that will be the sequence of their phases, ABC and CBA. Okay, that is a double circuit line. So let's say a fault has occurred in phase A to ground in line 1. So the flow of fault current will be like this. Fault current, a portion which I have shown with the solid line, is directly flowing into the fault from bus 1, and fault current which I have shown with dotted line is being contributed by this bus 1 through the line 2, phase A of line 2. In the presence of this fault, if a short circuit occurs in phase B of the parallel transmission line, that is known as cross country fault. when lines are very close to each other, a flashover in one line may result in a flashover in a parallel line as well. That is known as a cross-country fault, and that is a very common phenomena in multi-circuit transmission line. Multi-circuit transmission line means multiple three-phase circuit along the same tower. So that happens very often, that fault in one line is extended to the fault in the parallel transmission line. And what had happened here in this particular example, there was initially a single line to ground fault in phase A of line 1 that has extended to a line to ground fault in phase B of line 2. So what will be the direction of flow of current in this phase? So this solid color line which I have shown, that is the direct contribution towards this fault from bus A, and here is a contribution that I have shown with dotted line that is being contributed towards this fault from bus A through bus B. Now the simultaneous existence of these two line to ground fault will result in a fault current in phase B and phase A. So this fault will appear to be a line to line fault for both lines, in line 1 as well as for line 2, because fault current is existing in both lines A and B here in line 1 and line 2. So what will be the net impact on the protection? Instead of considering it a line to ground fault, relay would consider it a line to line fault. Although tripping will be done, then what's wrong with this operation? Ultimately we want tripping of the circuit breaker. Remember here, if we are following three pole operation of the circuit breaker, nothing is wrong with this problem, because we are going to trip all the three phases no matter what is the type of fault. But if we are practicing single pole operation of the circuit breaker, that is problematic, because in case of line to ground fault, tripping of only faulty phase was required. That will follow by the immediate reclosing. But due to this simultaneous existence of fault current, now this fault would be considered as a line to line fault. So all the three phases will be tripped. So there is a confusion in post fault analysis. What was the reason of tripping of the line? And that is due to the cross country fault, where fault produced in phase 1 of one line that has extended to the second line, and their simultaneous existence has converted this line to ground fault into a line to line fault, and that would result in misjudgment of fault. So I'm repeating it again. If the tripping practice is three pole operation of the circuit breaker or three phase operation of the circuit breaker, nothing is wrong here with this fault. No matter what is the type of fault, all the three phases will be tripped. But if the practice was to trip only the faulty phase in case of line to ground fault and all the three phases for any other type of fault, so yes, here for line to ground fault all the three phases would be tripped, and there will be confusion in post fault analysis. So post fault analysis is very important, because we want to know what was the reason of tripping of the line, so that if it is incorrect tripping of the line, some solution could be advised to avoid this incorrect tripping. Or if protection has failed to clear the fault, then we will have to change the setting. So now in numeric relays, many algorithm has been developed to figure out this situation, so that proper tripping of the circuit breaker will be done according to the situation. But electromechanical relays cannot differentiate between these two situations. They will always misoperate. So that is the end of the lecture. Here end problem from 5.1 up to 5.11 are included into your course. Here is the excluded article 5.4.3 relays in unfaulty phases, and there is an other excluded article, that is zero sequence coupling in distance relays in parallel transmission line. Article number 5.9, that is also excluded, but its sub articles 5.9.1 and 5.9.2. These two are included and that we have just discussed. These two are part of the course and here it is excluded.